Hello, and thank you for being here. I'm Francesco Sgherzi, a master's student in computer science from University of Illinois at Chicago, and today I'm going to present to you Learning Lines with Ordinal Constraints, our paper for the Approx 2020 conference by Bohan Fan, Diego Ihara, Nestat Mohammadi, Anastasios Sidiropoulos, Mina Valiside, and I. The course of dimensionality has shown us that the higher the dimensions of the dataset, the harder it becomes to retrieve meaningful patterns from it. That's why geometric methods such as KNN or PCA have seen widespread adoption as the first stage of the analysis in order to assess some relevant patterns in the data points before carrying on with the additional analysis or classification and regression. The key takeaway of those approaches is that they encode every data point into a less featureful space while still preserving some relevant pattern of the dataset and therefore render a subsequent classification or regression task much easier. These methods, however, rely heavily on the metrical representation used to encode the data. That's why many techniques such as metric learning have seen rise in usage due to the fact that they can learn a good metric that well suits the structure of the dataset and possibly makes subsequent tasks more streamlined. Starting from a generic dataset, we encode similarity and dissimilarity informations in ordinal constraints. In fact, the input to our problem consists of a set of points and a set of ordered triplets of points, representing the fact, for instance, that the first element of the triplet is more similar to the second than the third. Given a point set X, a constraint set T, some space Y which is metric with some distance function ρ, we want to find a mapping from the point set to this metric space such that for all triplets the distance in the mapping between, let's say, the image of 0 and 3 is less than the distance between the image of 0 and 6. We refer to this problem as learning a line metric space under ordinal constraints, or LLOC for brevity. More specifically, we study the case of a dense instance, meaning that every constraint between data points is defined in our constraint set. Note that, in general, there may not be a solution which satisfies all the constraints. Think about the case of having just 3 points and the following constraints. In this case, by exhaustively enumerating all possible embedding, as seen in this example, one can easily see that, for instance, the first embedding violates the third constraint, the second also violates the third constraint, and the last one violates the second. In the case where a solution that satisfies all the constraints exists, we refer to it as the perfect information case, while if it doesn't exist, we refer to it as the imperfect information case. In the imperfect information case, the objective of the problem becomes to find a solution that minimizes the number of violated constraints. This is pretty much an active field of research. More specifically, many advancements have been brought in the case of contrastive constraints, which is the problem of learning a metric space where relations between points are expressed by similarity and dissimilarity constraints. In this setting, the goal is to create a mapping F from X to some metric space M with distance ρ, such that for every element of the tuples in the similarity set S, their distance in the embedding is at most some upper bound, and for every element in the tuples of the dissimilarity set D, their distance in the embedding is at most some lower bound, up to a small multiplicative factor. Embedding into the line is the simplest instance of dimensionality reduction and has also been extensively studied with various objectives up to minimize to multiplicative, additive, or average distortion. Another problem, which may seem similar to ours, is the Betweenness problem, in which, given a dense set of ordered triplets, it aims to find a bijection G from the point set to the point set itself, such that G of B appears between G of A and G of C. While the problems may seem similar, there are a few distinctions. A first difference is that the ordinal constraints does not imply any ordering constraint. A second one is that the ordering of the points most of the time is not enough to recover a nearly optimal embedding that respects the constraints. Therefore, our problem has much bigger span. Here, we present our contribution. This is the main result of our paper, which is an algorithm for solving the general case. meaning that we can handle both the perfect and the imperfect information case on dense instances. The intuition behind the algorithm is the following. We first start by guessing the leftmost point in the optimal embedding, and from that we can reconstruct the optimal embedding by exploiting some information contained in the constraint set. This, however, leads to a big distinction between the perfect and the imperfect information case. In the perfect information case, by guessing the leftmost point, we are sure that it will not be involved in any violation of constraints, and therefore we can construct the embedding by simply checking which point is constrained to be closer or further from the leftmost point and extending the information to all other points. In the imperfect information case, however, this is not true anymore. In fact, the leftmost point is involved in a certain small number of violations, and therefore we cannot reconstruct a good embedding by comparisons as we did before. So, as a warm-up, we first introduce a simple algorithm for the perfect information case. For some optimal mapping, we can guess the leftmost point on the line, and then, for all points in our point set, we can decide which comes before and which comes after, based on which constraints is in the constraint set. After that, computing the optimal embedding can be done by computing a feasible solution to the following LP. Note that, by using an LP as a mean to retrieve the embedding, we can correctly identify a posteriori if we are handling the perfect information or imperfect information case. In the case that the LP is infeasible, we find ourselves in the imperfect information case, and therefore we need to use another algorithm to find the solution. Now we show a sketch of the algorithm for the imperfect information case. As we did before in the perfect information case, we begin by exhaustively guessing the leftmost point. Note that, as I've said before, we cannot blindly reconstruct the embedding by comparisons, so more steps are needed. After that, in fact, we create a tournament where the node set is the original set of points, and the edge set contains the edges ij if the constraint involving the leftmost point is in the constraint set. After that, we compute an O of 1 approximate minimum feedback arc set, and since now the resulting graph is acyclic, we can compute a topological ordering of the nodes. The rationale of these steps is the following. If I guess the leftmost point correctly, it will only be involved in a small number of violations, and therefore, by creating a tournament and doing the feedback arc set, we would remove all those backward edges that imply a violation of the constraints. Now, we ought to create a smaller, simpler instance, which we call retracted instance, by assigning n over b contiguous points to b buckets and creating a new set of constraints between buckets which are appropriately weighted by the number of original constraints across involved buckets. Finally, since the number of buckets is now constant, we enumerate exhaustively along all possible embedding, all possible solution, and we output the solution that minimizes the weight of the violated constraints. Now we will present a little analysis of the steps that bring this algorithm to life. We first begin by defining a point to be alpha good if it's involved only in a small number of violations. Then we claim that in fact this point exists and its location is in the first 2 times square root of epsilon times n points. The demonstration is quite intuitive and it's as follows. Let xi be the number of violations in the optimal embedding. Then, by definition, since the problem admits a solution that violates only an epsilon fraction of the constraints, xi is constrained to be smaller than epsilon times n minus 1 choose 2. Now, suppose that this point does not exist in the first indexes of the embedding. This would mean that all of those points are involved in at least square root of epsilon fraction of violated constraints, which would imply that xi is actually bigger than the maximum number of violated constraints, which is a contradiction. Now we map this point to the first position. It can be shown that this point is alpha good, and remapping introduces only an additive fraction of additional violation, which is proportional to 1 over n. Now, recall that as the second step of the algorithm, we created a tournament as follows. The vertex set is the original set of points, and the edge set contains points ij if the constraint I star I, j is in the constraint set. Now we need to demonstrate that the embedding obtained by removing the violated constraint is not only a topological ordering of the nodes, but also the number of edges removed is small, and therefore this embedding can be obtained by computing the feedback arc set on the created tournament. The demonstration of the size follows by the definition of alpha goodness. If the point I star is 1 minus square root of epsilon good, then it's involved in at most square root of epsilon fraction of violation, and therefore this is the maximum number of edges that are removed. It remains to demonstrate that the resulting embedding is a topological sort, and therefore it can be obtained by solving the feedback arc set on it. Note that by first moving an alpha good point to the first position and then constructing a tournament, the violated constraint would generate edges that are involved in cycles. By removing those backward edges, the resulting graph would be acyclic and therefore induce a topological ordering of the node, and this concludes the proof. To obtain a topological sort of the nodes, it is necessary to compute a feedback arc set, which is a well-known NP-hard problem. We will later show that it suffices to compute a constant factor approximation feedback arc set in order to achieve a good embedding. Now we are reaching the final steps of the algorithm, and we have created a retracted instance of the problem. The key concept of the retracted instance is that we condense points that are close in the embedding into buckets, and we treat all of them as one by choosing a representative. This step, however, is not completely painless. It implies that in some cases, this procedure introduces some new violation and doesn't necessarily fix some of the violation that we had before. For this reason, we introduce the concept of stable and unstable buckets, which, informally speaking, defines the fact that a bucket is stable if the points contained in it appear somewhat consecutively in the embedding, and unstable if there are some intervals in the optimal embedding separating the points in the buckets, so the points appear interleave with some intervals in the optimal embedding. Of course, one can easily see that unstable buckets are the one which create the biggest problem, so assessing the number of them is a crucial step in our analysis. One can show that if a bucket I is unstable, it must contain many of the points which were involved in an edge cut by the feedback arc set algorithm. So, let J be the set containing all indices of the unstable buckets. We will show that J is small. In fact, for a bucket to be unstable, the feedback arc set should have cut many edges which had an endpoint in it, and therefore, by dividing the total number of edges cut by that number, we obtain the number of unstable buckets, which fortunately is still small. After that, the only remaining step is to exhaustively enumerate all possible embeddings and outputting the one minimizing the weight, and by extension the number, of the violated constraints. This step obviously does not add any additional violation. Okay, now we finally reach our last step of the analysis, and we need to count how many additional violations our many steps have introduced. So, first of all, we have the constraints that cannot be satisfied a priori. This is a property of the given dataset, and there's pretty much nothing that we can do. The second component that adds some constraint violation are the constraints in which any of the 2 points falls into the same bucket. Those points get mapped to the same representative and therefore to the same point in the embedding, thus violating their constraints. The third component are those constraints whose points belongs to unstable buckets. The fourth component are the points for which the bucket they belong is involved into a brittle triplet. A triplet is brittle if the choice of the representative for each bucket involved in the triplet does matter and thus influences the number of violated constraints. The proof of the number of brittle triplets has been omitted in this presentation for brevity, but can be found in our paper. The last component that adds violation are all those points which we define as nosy. Recall that for a bucket to be stable, we allow only for a small fraction of points in the generating interval not to be contiguous in the embedding, and this is the result of that. The demonstration, once again, has been omitted for brevity. Now, let's walk through each contribution. The first contribution we have some influence on is the points that are in the same bucket and therefore gets mapped to the same point in the embedding. But how many of them are there? Well, fortunately, only a small fraction, and the demonstration leverages the result obtained in the feedback arc set. The second contribution is represented by those constraints which point belongs to unstable buckets. However, we have already demonstrated that the number of unstable buckets is small and, by extension, the number of added violations is small. The third contribution is represented by all those constraints which have points in the buckets that form a brittle triple. As said before, the demonstration of the upper bound of the number of violated constraints from brittle triplet can be found in our paper in section 5, and fortunately is still small. Lastly, we assess the contribution of the noisy point. This, along with brittle triplets and unstable buckets, represent the biggest contribution to our constraint violation. For the final count of the violated constraints, it suffices to sum up all the violations, since all of them are additive, and therefore we notice that we are in fact limited by the influence of those noisy points. Finally, it remains to bound the time complexity. A two-main operation are here the feedback arc set, which takes big O of n to the power of 6, and the exhaustive enumeration, which take big O of n to the power of 3n. All those operations need to be computed for each point, as this is our guessing of the response point, and therefore here we show the final time complexity. Okay, so now we have reached the end of this presentation. I would like to thank you all for your attention. This is our context, so feel free to send us an email if you want to ask more questions, and see you at XProx 2020.